So before we start with the observations, I just want to talk a little bit about what we see here. So basically the idea is that we have an observer. For a flat Earth, he's centered at the North Pole. On the globe, he could be centered anywhere because of the symmetry of the globe, but let's put him at the North Pole. And we can raise the observer height, and we'll look at how it affects the angle between the straight line, which is this red line. We'll look at that in more detail later, and the horizon. I'll come back to these two different angles when we look at the observations. But let's look at the flat Earth case first, because here we have this point is the rim or the edge of the world, if you believe in a flat Earth, or the ice wall or something like that. And on the globe, that would be, you know, the South Pole. We see that if the observer is at 100 kilometers height or elevation, we see that this angle isn't zero. So even on a disk world, if you will, this angle is not zero. In fact, it would become zero only if we extended the distance to said rim to infinity. And so we see that at sea level, or for an observer 2 meters above the ground, this, for all practical purposes, the distance horizon on the flat Earth would rise to eye level, because this angle is for all practical purposes zero. But there should be an angle observable if you get high enough. You should actually, if you have like a very powerful telescope and you're, let's say, at an altitude of 100 kilometers, you should see the great wall of ice here at the rim. So the main point here is that if it's not an infinite plane and things are infinitely far away, this angle between the straight level line from the observer to the rim here, it will be non-zero. So let's zoom in and look at the cases. And now I just want to mention these two different circles here. So this black one is a circle with the radius of the Earth, what we believe the radius of the Earth is. So that's gonna be what we call the geometrical interpretation, which means we don't care about refraction. This blue-green thing here is a circle with a bigger radius, and we use that as a model for how distances and how things look if we take refraction into account. Okay, so here we see the two horizons. One which is the refracted horizon and one which is the geometrical horizon. Which is the one where we don't care about refraction in the atmosphere. So this is how it looks like. We can remove the line to the flat Earth horizon. You see that at this observer height we have an angle between this red line and the line to the geometric horizon is 0.43545 degrees, and we have angle to refracted horizon is 0.40315. Okay, so let's look at observation made by Wolfie.
So in this video I'm going to show you footage of a sunset taken from 45,000 feet in an aircraft with the theodolite app in my iPhone. As you can see, I have the crosshairs pointed at the sun, which is setting right on the horizon, and the app is indicating an angle down of 3.7 degrees.
So in his video he's like 45,000 feet in the air, and that translates into approximately 13.7 kilometers. And we see that we have these two angles to the geometric horizon and refracted horizon. And since this is far from low altitude observation, the actual observation that Wolfie makes is very close to this one. So to summarize, we see that this model, the model of a globe, it fits both at low altitudes when we can use this refracted horizon, if you will, this approximation, and it's important to remember it's an approximation, and for higher altitude observations we see that actually using the pure geometrical model fits nicely. And actually none of the observations matches a flat Earth model.